The science and culture of hair. Speaking of hair and beards, why do we need to shave our beards or cut the hair on our legs while other animals don't? I believe we are trying to ask three different questions here. First, why do other animals not need to shave their hair and beards like us, while we have to do it regularly? Second, why do we need to cut only some of our hair? For example, why doesn't the hair on our head stay at a fixed length like the hair on our arms, but we have to actively cut it? Third, why do men and women have different amounts of hair in different places? Let's start by correcting the most common mistake about hair and feathers, because I still see terrible explanations on television. People, especially women, talking about their body hair and men referring to the fine hair that grows on their cheeks, always use the word tui, feather. There is no such thing as tui, feather, in humans. Feather is a highly scientific term and a structure found only in avian or flying dinosaurs. What are dinosaurs, you ask? Well, dinosaurs, specifically flying dinosaurs, are still alive. Birds, yes. The birds you see on the street today are the only group of dinosaurs that survived the mass extinction 66 million years ago. Initially evolved from differentiated skin cells for purposes like attracting a mate or maintaining body temperature, feathers today remain a distinctive feature only of birds. Of course, there are various types of feathers in birds, but ultimately they are all a keratin structure branching out around a single shaft. But in short, if you find a feather, you can be sure it belongs to a bird, not a reptile, a mammal, or an insect. On the other hand, all mammals have another keratinous structure called kul, hair. Hair is a much simpler structure than a feather, and is found only in mammals like humans, deer, cows, lions, cats, and dogs. Hair is usually just a single shaft, and the differences between different hair types are determined by the thickness of that shaft or how it bends. If an animal has this structure called hair, it must be a mammal. And if an animal is a mammal, all of its hair, whether thin or thick, must be called hair. For instance, even whales, which are marine mammals, have hair, albeit highly vestigial. Of course, you may have seen hair-like structures on insects like bees or arachnids like spiders, but theirs are made of chitin, not keratin. They are entirely different structures and are not considered mammalian hair in the true sense of the word. In summary, every hair on the human body, from the thinnest to the thickest, from the straightest to the curliest, from the whitest to the blackest, is called kul, hair. There is no such thing as thin ones being tui, feathers, and thick ones being kul, hair. Of course, this makes expressions like, "my feathers are standing on end," a bit difficult, but we'll forgive it as an old idiom passed down from our ancestors. The evolutionary reason for our nakedness. This issue of thinness and thickness reminds us of a more interesting fact. You know that although we have extinct closer relatives like Neanderthals and Denisovans, our closest living relatives are chimpanzees. But they are so hairy and we are so hairless, aren't we? We did not evolve from chimpanzees, but based on the fact that our more distant cousins are all hairy, it's not hard to see that our common ancestors, who lived in environments similar to our current cousins about 6 to 7 million years ago, were at least as hairy as chimpanzees. So did humans lose their hair? No. Humans and chimpanzees still have the same density of hair on their bodies, about 60 hairs per square centimeter. But the reason we look so much more naked than they do is that our hair has become vestigial in thickness, not in number. The same amount of hair being much thicker in one species and much thinner in the other makes one look much more naked than the other. In fact, some mutations in humans can reactivate the genes that produce that thick hair, which are still in our genome, leading to a condition called hypertrichosis, or excessive hairiness. But if you've noticed, our bodies aren't entirely naked. Our species' hair, especially on the head, underarms, and pubic areas, is still clearly visible. The hair on our arms and legs is also noticeable in both sexes, but in many societies, women and increasingly men shave or remove this hair for cultural reasons. Similarly, as our French friends know well, whether or not to shave pubic hair, and in what style, varies greatly from culture to culture and from era to era. Additionally, in men, hair on the face, chest, and back is thick enough to be easily seen. There is a whole industry dedicated to getting rid of this hair that grows in different amounts in different places. Think of barbers, hairdressers, or laser hair removal centers. This situation shows that in the evolutionary process, hair all over the body did not change as a single group. The hair on our head is hair, and the hair on our arm is hair, but their growth amount and thickness are different. This is actually the main answer to all the questions we asked at the beginning. The length and thickness of hair are not controlled by a single gene throughout our body. On the contrary, more than 350 genes have been found to influence the physical properties of our hair. The effect of a few of them, such as LHX2 and DNMT1, is more pronounced. But as a result, in the evolutionary process, we specialized in having hair of different qualities in different body regions. The evolution of different combinations of these genes can create animals with completely different levels of hairiness. These genes, of course, affect details like hair thickness and how often it is produced per square centimeter. But these genes also determine how long a hair will grow. The mystery of hair growth and why we're not like lions. This brings me to another question. Why don't other animals have this? Why doesn't a lion have to cut its mane while our hair can grow long enough to get tangled around our feet if we don't cut it? Actually, this question is based on a false assumption, because no one's hair, except for individuals with some genetic problems, grows forever. Let me explain. All the hair on our body goes through 4 phases. The anagen phase is the phase where our hair is produced. In this phase, all the hair on our body grows by about 1 centimeter per month. This is slightly faster in men than in women. The anagen phase usually lasts for a maximum of 7 years, but in some people it can go up to 8, 10, or even 15 years. The hair of these individuals, which is not always abnormal, can grow much longer than that of an average person. This is one of the factors that contributes to the myth of infinite hair growth, but they are a minority. In short, the longer a hair stays in the anagen phase, the longer it grows. For example, about 85% of the hair on our head is in this phase at any given moment, and this hair can remain in this phase for years. However, the hair on our arms stays in the anagen phase for only 1 or 2 months. This is why the hair on our heads can grow much longer than the hair on our arms. And of course, because we usually cut the hair on our heads before 7 years, we assume it would grow forever if we didn't cut it. This is not true. After the anagen phase, hair enters a transition phase called the catagen phase. This phase lasts for about 10 days, during which the hair follicles that produce the hair begin to shrink and slow down hair production. After about 2 weeks, the hair and the hair follicles separate, but the hair is still not shed. About 5% of the hair on your head is currently in this catagen phase. After this comes the telogen phase, which lasts for about 3 months. You can think of this as the about to fall out phase. The hair is no longer growing, but it hasn't fallen out yet. About 10% of the hair on your head is in this phase. Finally, in the exogen phase, the hair can no longer hold on and falls out. This phase is much shorter and causes you to lose about 50 to 100 hairs a day. After this, the hair follicles return to the anagen phase and start producing hair again. The duration of each hair in each phase is determined by the hundreds of genes I mentioned earlier. But ultimately, what determines which species has which combination of these genes is, of course, evolution. The growth duration of hair in all animals, including humans, is determined by evolutionary mechanisms that have selected and eliminated certain gene combinations over generations. However, the idea that other animals don't make hair adjustments like humans is also a completely false notion. For starters, those who have a cat or a dog at home have seen their animals change their fur with the change of seasons. Or a lion's mane, just like human hair, grows much longer than its other hair, but neither human hair nor a lion's mane grows forever. Both have an upper limit, and at some point these hairs can break due to mechanical effects like friction or snagging, or because the hair is not healthy enough. Or the faces of orangutans, which are normally a ball of hair, are completely hairless. So you see, we are not as different from other animals as we think. In them too, for evolutionary reasons, hair grows or doesn't grow in different ways in different places. But thanks to our intelligence and our culture, we can intentionally intervene with our hair and style it. This is the only difference. Natural and sexual selection. This brings us to our second question. We said that evolution determines where and how much hair grows on our body, but how exactly does this process work? Why is the hair on our bottoms, not our heads, completely shaved off? What's the difference with our face, armpits, or private parts that hair was preserved here? The answer is twofold, and each answer corresponds to one of the most important fundamental mechanisms of evolution: natural selection and sexual selection. Understanding the natural selection part is not very difficult. In the wild, individuals who produce excessive hair for any reason are quickly eliminated because they cannot easily escape from predators, catch their prey, or even use their limbs easily, and therefore do not pass on the genes that make them excessively hairy to future generations. Similarly, in species that need to produce hair to warm up or to camouflage, if a mutation that prevents hair production occurs, those extreme individuals are also quickly eliminated. This way, the hair length stays within the optimum range for that species and that environment. We call this type of natural selection stabilizing selection because it always tries to favor the average values and eliminates the extremes. By the way, one often overlooked function of hair is to help us feel deadly insects, like mosquitoes, before they can reach our skin. In fact, our hair actively protects us from these insects, so hair is not a structure to be easily lost. When we get cold or scared, our feathers stand on end just like our close cousins or distant relatives like cats, don't they? The purpose of this, if we are cold, is to increase the amount of trapped air between the skin and the hair to provide thermal insulation. If we are scared, it is to make ourselves look bigger than we are. Of course, with the reduction of hair in us, the tiny muscles at the hair follicles, called the erector pili muscles, have also atrophied. So this bristling happens very little and remains at a pitiful, ridiculous level. But still, it is very important to understand why we have such a reflex. But there is a third leg to the natural selection side of things. As I told you in a previous video about human evolution, one of the most important steps in human evolution was the widespread distribution of our sweat glands throughout our body. This is because sweat glands served as an excellent heat regulator for our species, which was able to migrate over long distances. For example, in chimpanzees or orangutans, who generally prefer to stay in the same region, sweat glands are almost entirely clustered on their palms and soles. In us, however, the eccrine sweat glands, which open directly to the skin surface, are widespread. Let me show you on an evolutionary tree. This graph shows the distribution of sweat glands on the bodies of humans and all our close relatives. Red is close to 0%, green is about 50%, and dark blue is 100%. Does one species catch your attention? Yes, that's us. But because eccrine glands open directly to the skin surface, they cannot function well if there is hair there. Therefore, in the last 6 to 7 million years of evolutionary process, Our hair thinned out to make room for our sweat glands, and this allowed our sweat glands to spread over an even wider area. But some hair was under a strong opposing selective pressure enough to resist this natural selection. Our head, face, armpits, and of course our pubic areas. Why? Well, this brings us to our third and final question. Why do men and women have different amounts of hair in different places? There are very good reasons for why some hair is preserved in different sexes and why some hair changes in a sex-specific way. The power of sexual selection and the purpose of hair, for example, the hair on our heads is dense in both sexes. While sweat glands are very successful in cooling the body without hair, hair is also very good at keeping the temperature within a fixed range as long as extreme conditions don't occur. Why is it so important to keep the temperature of our head stable?
Does an organ that might need this come to mind?
Yes, our brain. Because it is very important to keep the temperature around the brain stable, the hair on our heads has remained even denser than in our small-brained ancestors. The hair on our armpits and pubic areas has one more function from the perspective of natural selection, which I skipped. In places with a lot of friction, hair acts as a lubricant, reducing wear and tear on the skin. Therefore, the preservation of hair between our rubbing parts is very important. But at the same time, the second fundamental law of evolution comes into play here: sexual selection. The males and females of our species selected each other based on the presence of hair in certain areas. This was not always a conscious choice. For example, hairiness on the armpits or face signaled that an individual had entered puberty and was of reproductive age. Therefore, these characteristics, which we call secondary sexual characteristics, were inevitably selected. Hair on men's faces was selected over generations by females as both a sign of reaching reproductive age and, according to some studies, a symbol of power. Similarly, males selected females for generations to have a younger, fresher appearance, and therefore more baby-like, smoother-skinned, and less hairy female bodies were selected. A secondary reason for the preservation of hair in the pubic and armpit regions is the sexual pheromones, or sex-related odor hormones, that are still thought to be secreted from here. In hairy areas, these aphrodisiac-like hormones are thought to be dispersed more controlled, and therefore they are thought to have increased our species' sexual success. Hair on the arms and legs also reached today with a wide variety within our species, due to different amounts of sexual selection pressure. And so, we started with hair and ended up in entirely different places. But as you can see, we can learn a lot about our species' past and the breathtaking dynamics of nature, even from something that seems as insignificant as hair. Even the simplest questions we ask in daily life whisper to us the secrets of nature. And by using what we learn here, we can solve the challenges we face in completely different areas. I think this is exactly what makes science so exciting. See you in the next video. Goodbye.